Hi, my name is Caleb Serafy from the Electrical and Computer Engineering Department of the University of Maryland. I'm doing my PhD under the guidance of Ankur Srivastava, and this is our work titled Unlocking the True Potential of 3D CPUs with Microfluidic Cooling. In this work, we study 3D integrated circuits, which are created by taking traditional integrated circuits, stacking them vertically, and connecting them through silicon vias. Now, such an approach has some significant advantages that we want to leverage, but that also comes with some significant disadvantages that need to be overcome. In this work, we specifically look at the increased power density and trapped heat effect of 3D integrated circuits. 3D integration can facilitate new 3D architectures through heterogeneous integration of different manufacturing technologies, increasing the bandwidth between each component, and increasing the overall transistor density. 3D integration requires electrical isolation between each layer. This has the unintended consequence of also causing thermal isolation, which traps the heat produced in the intermediate layers from having a low resistance path to the heatsink. To design around this, each intermediate layer will have to be designed with a low power dissipation, which can severely limit the potential performance brought with 3D integration. Microfluidic cooling is an aggressive cooling technique that can overcome this problem by pumping fluid between each layer in the stack. This type of cooling can scale with the number of layers and can reduce leakage power, improve energy efficiency, and make new 3D architectures thermally feasible that otherwise would not be. In our work, we simulate the performance, power, and temperature using a leakage feedback model of 3D integrated circuit computer architectures. We simulate DRAM over logic structures, where cores, caches, and memory controllers are integrated below layers of DRAM, and the DRAM bus is implemented using a TSV array. When we run our simulations, we can change the core frequency, the amount of memory parallelism, which is to say the number of memory controllers and DRAM buses, and the number of cores. We simulate temperature using a thermal resistance network, which takes advantage of the duality that exists between electrical and thermal differential equations. For each architecture, we simulate the temperature using two structures, an air-cooled and a microfluidically cooled resistor network. We perform two different simulation flows, the first of which considers parallel workloads. We use benchmarks from the Parsec and Splash2 workload library. In this first simulation, we first fast forward through the sequential part of the benchmark and only simulate through the parallel portion. We identified the best architecture for each benchmark that's subject to the constraint of maximum temperature less than 85 degrees Celsius. We optimize both for performance and for energy efficiency. When optimizing for performance, we can see that by using microfluidic cooling, the best performance achievable is almost double what can be achieved with air cooling. We also see a slight increase in energy efficiency. When we optimize for energy efficiency, we see about a 1.5x increase to both energy efficiency and performance by using microfluidic cooling as opposed to air cooling. Our second simulation flow uses the same benchmarks, but instead of fast forwarding through the sequential portion, we simulate the sequential and parallel portion for a fixed number of instructions. Now, each benchmark is going to have a different ratio, which we denote as alpha, between the sequential and the parallel instructions. You can see that we've simulated a large variance from very low to very high alpha values. Now, the optimal number of cores for those benchmarks that have a high value of alpha is very high, but for those with the low value of alpha, the optimal number of cores is quite low, and the only way to improve the performance of these benchmarks is through frequency scaling, not core scaling. Similar to simulation setup 1, in this setup we also show that microfluidic cooling can unlock much higher frequencies and in some cases higher core counts to improve performance and energy efficiency. If we look at the results for energy efficiency and power versus frequency, we can see that with air cooling alone, which is the dotted line in these figures, that energy efficiency might actually decrease with frequency. When we add microfluidic cooling, it can reduce leakage power to such an extent that energy efficiency actually increases with frequency. This slide shows the amount by which leakage power and energy efficiency can be improved by using microfluidic cooling in 3D ICs. We can see that as frequency increases, the amount of this improvement also increases, giving good motivation for using frequency scaling in microfluidically cooled 3D ICs. In conclusion, We've shown that microfluidic cooling can unlock the true potential of 3D CPUs by facilitating much more aggressive computer architectures. We've also pointed out that frequency scaling is often the most effective scaling method as opposed to core scaling because many benchmarks contain a low level of parallelism. The frequency scaling trends of 3D CPUs with microfluidic cooling are much more attractive than those with air cooling, giving further justification for why microfluidic cooling is needed for future 3D CPUs.